Hi again, guys. Well, happy vacation. These things should keep you going from going through math withdrawals. So let's begin. Okay, here's board problem 36. A die is loaded so that the number 6 comes up 3 times as often as any other number. So what's the probability of rolling a 1 or a 6? Okay, remember, you can pause this wherever you want to. I'm trying to go fast so it doesn't make these videos too long. Okay, so this is how I thought of this, you guys. There's other ways to do this. Okay, since they're disjoints means you can't get a 1 and a 6 at the same time. So they're mutually exclusive from each other. So the probability of 1 over 6, you just use the addition rule on that. If it was a regular die, then each number, 1, 2, 3, 4, 5, 6, would have the equal chance at coming up. But the 6 occurs 3 times as often. So you have to write a couple of more 6s in this category because there's 3 of them that comes up with only one of all the other ones there. So that's going to create 8 numbers. So the probability of pulling a 1 is 1/8. Probability of pulling a 6 is 3/8. So 1/8 plus 3/8 equals 4/8, and you get 1/2, choice C. Hooray! Okay, so here's 7.1-2. This is the second lesson, continuous random variables, and we're going to do, remember when we did a normal distribution with mean, mu, and standard deviation, sigma? Remember those symbols? Well, we're going to come back to that shortly in this lesson here. So think of all numbers x such that x is between 0 and 1 inclusively. Inclusive means he has the equals bar on it, okay? You're including them. So how many numbers are there? Well, there are infinitely many numbers. Infinite is a sideways 8, so there's infinitely many numbers. 0.1, 0.2, 0.123, 0.125, 0.12, 0.2, 0.4, 0.5. I can keep going and going, but we want to make this video short. So there's infinitely many. So then how can we assign probabilities to such events such as the x values between 0 and 7 inclusively, where all possible outcomes will be equally likely? Well, what we have to do is think of our density curves. So remember, density curves, you guys, is a curve where the area always equals 1, you guys. So if we think about this, the random number and the uniform distribution, and so I'm going to show you with an example, 7.3 on page 398, section B. So here it is. The random number generator will spread its output uniformly across the entire interval from 0 to 1. All right, now I'm going to just show you the picture. I'm going to jump right to this picture right here. Okay, in this picture, here's the picture from 0 to 1 right here. Notice this height is 1. So if this was my density curve would be 1 times 1. Remember from geometry, base times height? So the area of this square is 1. Okay, so the area of between 0.3 and 0.7, this base would then be, would be 0.4 right there. Okay, so 0.4 times 1 would be equal to 0.4. Okay, that's how we're going to get around this on this. So because the area under density curve above is the interval from 0.3 to 0.7 is 0.4. All right, remember base times height? That's all that says right there. Similarly, if I asked you, what's the probability of your x being less than 0.5 but greater than 0.8? Okay, well, 0.5 and 0.8, they don't overlap each other, so you can just add those areas, and here's the picture that shows that, you guys. So from 0.5 to 0.8, remember this is still height 1 right here, and so if this is 0.5, so 0.5 times 1 would be that area, and from here this is 0.2, so 0.2 times 1, so you'd add those together and you get 0.7. So to answer this, what's the probability of x such that it's less than 0.5 or greater than 0.8? It's going to be 0.7. Yeah. Okay, so here's section C. A continuous random variable x takes on all values in an interval of numbers. So the probability of any event in any interval is equal to the area under the curve in that interval. Okay, just what we just did right there. Individual outcomes are assigned 0 to continuous probability distributions. So for example, you guys, say I wanted to know what's the probability of the interval at x equals 0.8. Well, at x equals 0.8, it's just a straight line, and the width of that baby would be 0. So the area would be 0 times 1, or 0. Okay, so if it's just a number, if it's equal to a number, then the area is always assigned 0 on those. Okay, it has to be less than or in between some numbers. Okay. All right, so recall that, here we go, the normal distribution with mean, mu, and standard deviation, sigma, is the normal distribution with those symbols right there. Also, you remember this, you guys? The number in the front of our book, Table A, your z-score number is x minus mu divided by your standard deviation, where x is the number that you focus on and z is the number that you get from Table A. And that'll randomize everything to a normal curve with mean 0 and standard deviation of 1. Okay, we want to get this, so because not everything comes with a mean of 0 and standard deviation of 1. You know, a bag of Wheaties wouldn't come into that. You know, it comes into whatever, so we have to use this z-score formula right here. Remember all that stuff from before? So drugs in school, you bad boys and girls. See example 7.4 on page 400 and 401. Okay. So an opinion poll asks an SRS, which is simple random sample, of 1,500 American adults, a nice size, 1,500, what they consider to be the most serious problem facing our schools. Suppose that if we could ask all adults this question and 30% would say drugs, okay? I'm sure there would be other things. So, and we're going to learn later in chapter 9 when we come back from break that the proportion P, which is this right here, so this P right here, proportion 0.30 or 30% is 0.3, is a population parameter. And this is a P hat right here, you guys. See that little symbol right on top of that right there? It's written like this. It's a P hat symbol. So suppose that the proportion parameter of that population P hat of the sample who's answering drugs is the statistics that we're going to use this sample. So we're going to say we're going to get a sample here, right here, and we're going to that's going to be our sample one that's going to represent our population one. Sorry, I'm getting my tongue all twisted up. It's not that bad, you guys. We'll see in chapter 9 that the p hat is a random variable that has approximately equal to, don't worry, we're going to learn how to calculate this later, that distribution right there. And the mean 0.3 is the distribution is the same as the population parameter of the sample p, okay? So what we're going to do is learn how to calculate this. It's all old school. We've done this before, you guys. Don't let all these big words scare you. They would have when I was your age. That, right there I would have said, blah. Okay, so when is the probability that the poll result differs from the truth about the population by more than 2 percentage points? Okay, so here's a picture that's by more than 2 percentage points. Some of this picture, we don't know where we got it yet. I'll tell you in just a minute right here. But I'll tell you, here's my 30%, so take off 2 percentage points would be over there. So we want this area by more than 2 percentage, so to the left. And then up here, notice 30%, so add 2% is 32% and more. So I want these two areas, 28% and 32%. Okay, well, I'll show you how to get these 0.045s in just a second, and then the 1.69s in just a second. So here we go. All right, so by the addition rule, for these are disjoint events because they're not overlapping each other, then we can say the probability that our sample proportion is less than 0.28 or greater than 0.32 is going to be, by the addition rule, we can just separate them up and add them together because they're disjoint events. Okay, they're mutually exclusive. So what we're going to do is we're going to standardize all this stuff and use table A. So it's all stuff we've done before. Remember this stuff, you guys? This is the number that we're going to focus on right here. This is my x number right here. So it goes x minus the mu divided by the standard deviation. Now they gave that to us, okay? So don't worry, that's given to us. Okay, so when you get that right there, you crank that out right there. That's where that negative 1.69 came up on. And then you go to table A, and on table A, look for negative 1.69, you guys, and you should find 0.0455. Okay, and then so, and that's my probability, guys, 0.0455. Okay, so when we do 32, that's my x. So x minus my mu divided by my standard deviation, and so we're going to get the positive 1.69. You get another 0.0455. Alrighty, so remember, by the addition rule, see, that's where we got these pictures right here. So there's that 0.0455 with the negative 1.69, and there's the positive 1.69. Okay, pretty groovy. Now that's where those numbers came from. Okay, so by the addition rule, we can go ahead and add those together. So we get 0.0910. Alrighty, so the probability that the same result will miss the true population by more than 2 percentage points ends up being 0.091, or about 9.1%. So that's a pretty nice size sample. So about 9% of the time it'll miss it by more than 2 percentage points. Okay, and I think that's it. That's it. So your homework will be on the side window next to this video.